Hi, everyone. I'm so happy to be here with you today. This talk is about database architectures, one of my favorite subjects, and yours too, I'm guessing, because you're here. And the title is Shifting from Capture First to Query First Database Architectures. If you don't know what that means yet, that's cool. We got this. Bear with me. I'm Rob Dickinson, CTO Resurface Labs, and I'm easy to find. My call sign on Twitter is @RobFromBoulder. And just a quick word about the bunny and the whale on the side of the slide there. These are little figures that you'll see come up again. Both projects very near and dear to my heart. The bunny is Trino, which if you haven't seen Trino is the successor to Presto. And Resurface is my home base, and that's the whale. So you'll see these critters pop up again a couple times in these talks. All right, our agenda for the next, about 50 minutes or so, leaving some time for questions, is really going to be a tour of the database landscape. We're going to introduce this idea of capture first thinking or capture first methods in database design. We're going to contrast that with more query first methods. So you really have an idea of kind of both sides of the coin there. I'm going to give you a framework or a method that you can follow if you want to try to do more of a query first project. That method is based on our own experiences, both positive and negative. Some of the projects that we've had that have gone sideways, and we'll get to talk about some of that fun stuff too. But the goal of this talk is to try to give you that simple method. And part of what you'll get along the way is a cheat sheet for database selection. So if you're thinking about starting a new project, doing some new functionality, whatever the context of that is, and you're wondering, of all these databases that are out there, how do I pick the right one for the right workload? I'm going to give that to you on one sheet of paper. Now, I can't start there because you wouldn't understand it yet. Like we need to unpack a little bit about why we need to be query first, why the database landscape is the way it is. But I promise you, I will do my best. If you go with me on this journey, in the end, we'll get you to a cheat sheet that I think will really come in helpful for future projects. So we'll see. Keep me honest on Twitter if I could have done better. So let's talk about databases. Certainly one of my all-time favorite subjects. So how many databases are there? I mean, this is a reasonable place to start, right? Especially for people that don't already know this material inside and out. How many databases are there? It's a hard number to get your head around. DB Engines is one of the great, I think, resources for tracking different databases and their popularity over time. Everybody argues about their algorithm at one point or another, but still, it's a good list. It's a great resource, and they're tracking 370 systems on that list. Right? It's crazy. I mean, how can anybody get their head around 370 different kinds of databases? And there's new ones coming all the time. All the time. We're a new one. Like there's always new room for growth in this market, and there's always people trying to do something new. But what that translates to, though, is a huge landscape to try to understand. If I'm a data architect or I'm a database architect or I'm a founder in something and I'm trying to think what kinds of databases, what kinds of storage, what kinds of processing do I need to be thinking about, the number of choices is completely overwhelming, and it's only getting worse over time. Now, there's some really smart folks who have done some really, really good work around how to visualize and classify these different kinds of databases so that people that don't necessarily see this all in color the way that you would if you're working with it every day can start to get a sense of what are the differences between these things, what are the similarities between these things, and how do they relate to each other. One of my favorite books on this subject is Designing Data-Intensive Applications by Martin Kleppman. Hope I didn't murder his name there, but huge fan. And he's done just some amazing work in this area that I think is easy to get your head around. You know, and I love this kind of visualization here. It feels like there should be orcs marching around here if you zoom in somewhere. And when you go into these kinds of analysis and these kinds of works, and very good ontologies such as this one, you'll see a lot of these databases being clustered together. Some of these are more similar than others, right? And that's really what we're getting down to here. There's a whole lot of databases that are out there, but there are cliques. So think about the number of databases. It's kind of like the high school, right? And then you've got the cliques within the high school, or with Martin's analogy here, you're laying this out topographically. We can talk about different kingdoms, different geographic regions, different territories that these databases are trying to occupy and distinguish from each other. And this is a really, really good resource for that kind of analysis. But I can't go on without just making two little tweaks with apologies to Martin, where it says presto here, right here. Trino is really the new presto. Oops, sorry. So I'm going to put Trino in presto's place there, and then Resurface, the database, would occupy kind of a space next to Spark. So yeah, okay, so this feels a little bit more complete to me now. Now I can keep going. All right, but let's step back for a second. How do we get to that crazy picture? A lot of people also will raise the perspective that, like, well, I thought there were just like, are you sure there's 370 databases? Because like, I thought there were just a couple of them, and the vendors were kind of chasing each other around. And I'm like, I'm pretty sure I've heard of Oracle, and like, right. And a lot of people kind of have this dated sense of what the database market is. They think the databases were conquered in the 90s or whatever. And they're really thinking, the way that they're thinking about the current landscape is just not true. Now it is true that millions of years ago, when I started building databases, the world looked a lot different, right? There weren't as many that were out there. You had these massive database platforms, and they were kind of the dinosaurs of their time. Not that these have died out, right? Obviously, we still have Oracle, we still have Postgres, whatever. But these versions of them have long since extinct. I mean, the modern versions of these things are nothing like what we had in the 90s, right? This technology's just continuously been refreshed. But again, if we're applying that like 90s thinking, long ago, this is what the database world looked like. And how do you do database development in Jurassic Park? Well, you do that database development for dinosaurs. And so if you go to most books about database management, database design, implementation, whatever it is, you'll see kind of the same patterns as far as how do you adopt a database, start using it, and implement it. And this is really, the classical way of thinking about databases. You're going to select your database platform. You're going to define what your schema is, what your tables are, your relations, all that stuff. You're going to start loading your data into this database. You're going to start integrating your applications. You'll get an increasing amount of capability out of all that. You'll start to see some performance problems, so you'll tune your normalization, you'll tune your indexes, you'll tune your queries. If things are really bad, maybe you'll add some materialized views on top or some query caching on top. And then if you just really can't get to the finish line, you kind of admit your fault as a data engineer, you switch platforms and you do something else. And again, I don't mean to impugn anyone who like looks at a classical book on database development and sees these kinds of recipes. This is still good. There's nothing wrong with this, but the world has really shifted from this kind of thinking and this kind of perspective. Most notably, selecting a database platform back in the day, this was the easy part. There weren't that many to pick from, and you tended to pick the one that you could afford, in the way that was the most comfortable to you. Like if you really had money that you were burning in a barrel at back, like maybe you'd buy Oracle. Um, Maybe you'd go Microsoft. Maybe you'd go open source if you could get the talent to help you with those open source databases. Because again, this is years ago. Um, there just weren't that many database choices. You tended to vote with your dollars. So this idea of like needing to select a database platform or selecting a database platform, to use a really bad pun, um, wasn't really something that you had to pay much attention to. It was something that you only did once in a while. It just and there really weren't that many things to choose from. It was a lot of times it was even pretty obvious what you'd be stuck with. The more you sit back from this though and think about it, there's some really tired thinking that came out of this, because this is really what we would call today capture first thinking. If you think about, like, well, step 2 here is all about capture, and step 3 here is all about capture, and maybe those queries are starting to come in step 4 or step 5, but those queries arrive pretty late to the story, right? You've got to build a lot of stuff to get to a place where you can assess that those queries are actually working. Now, I know what you might be thinking is saying, like, well, wouldn't you just test your queries as you go along, because you're a good engineer and you're a good developer and you're doing that kind of integration testing? Yes, absolutely. And you do that. But you're still hampered by the fact that you don't actually have a working system with a realistic data distribution until you get to the end of this process. Again, this is more waterfall. It's not highly agile. So those queries are coming into the picture awfully late. And that can get very uncomfortable. And it's one of the classic ways to fail in database development is to just focus on capture, and kind of kick the can down the road with queries, hoping that things will be okay, and then realizing in the end that you just couldn't get there. And everybody's seen projects that where that's happened. All right, so but that's the old world. So now we're looking at the new world. And in the new world, that first question of, well, what database do I pick out of that field of 300 and something, whatever, is crazy, right? That is not a trivial step anymore. You can't just pick Postgres and it's going to be the greatest thing ever for all possible cases. Not meaning to impugn anyone, but the world is a lot more complicated, and we just need to embrace that. So this is really, even for people that are going to spend a lot of time, years, trying to analyze this market and these vendors and these relationships, it still takes a lot to try to get your head around anything that's going to fit on a single piece of paper. So how do we manage all this, right? And you know that this is a problem because that's why you're here. That's why you're at this talk. How do you tackle this paradox of choice? One of my favorite coping mechanisms is you just go out for beers, you bribe someone to help you, you give them the context of what you're trying to do. They'll help you kind of navigate, yeah, you want orcs on this part and elves on that part, and they'll help you put that picture together. That's definitely a way to do it. And get that outside counsel. You can look at relevant benchmarks. You can look at things like TPC, try to find equivalent workloads, work backwards from that. That's a great way to go. Less less good ways of doing this would be, picking the one that you haven't used yet because you think that might be cool for the job you might have someday. Yeah, depending on the context, that may be a way to answer this question. You could also kind of stick your head in the sand and just stick to what you know. That's not really that fun either. You can put up that map on a dartboard and pick that way. You could do a magic 8-ball. Oh, if there was a magic 8-ball for this. God, I wish there was a magic 8-ball for this, especially for this audience. I can imagine that magic 8-ball like There's a lot of answers on there, but kind of Oracle is never the answer, for obvious reasons. I'd love to have that 8-ball. That would be awesome. But barring having any of those things to kind of make that decision for you, here's the better way to do it, and the way that you can do it independently and by yourself, without having to spend years and years and years becoming a database guru. So when you look at that giant diagram and you're thinking about where to start, what's the best way to pick a database, there's one way to do it, and that is you work backwards from what your target read workloads are going to look like. And let's just set for a minute. Read workloads. So we're going to prototype our read workloads. We're going to work backwards from that. And so that's really what we mean when we're talking about a query-first approach. We're starting from our queries, which are a lot of times the reads, right? We get that part right, and then we can work backwards from there. We can fill in all the other stuff that it's going to take to satisfy those reads. You can also think about this. It's kind of like test-driven development for database architecture, because in test-driven development, you're thinking about, what am I going to get out of the system? And you're really trying to classify that very, very specifically. Here's exactly what I expect to get out of the system. And then I'm going to work backwards to the implementation that actually delivers that. And we want to apply that same kind of thinking to our data architectures. This is more agile. But the primary way that we can apply this is to this idea of database selection. Because in all the things that you're going to read about with databases, there's a million tricks, there's a million tips, there's a million things. Once you've decided how to pick a database, then there's all the stuff that you can optimize with it. But how you pick a database is really an underserved topic. But this is how you get there. And so if you do get a chance to grab your favorite data architect and you pry the Mountain Dew out of their hand or whatever, and you take them out for drinks and you ask them to do this, this is the kind of approach they will more than likely walk you through. What is it that you're trying to do with this database? What kinds of workloads are you trying to run? And then we'll work backwards from that to the tools and the specific architectures or arrangements of those tools that would satisfy that. All right. Now, you may be feeling a little triggered, and that's okay. Just hang on with me for a second. So like all this emphasis on reads, I'm not saying that writes are bad. I'm not hating on writes. I'm not saying that you can ignore write performance either. What I'm saying, though, is that if you focus on reads, the writes will tend to take care of themselves. And it's a matter of perspective. So we're not really assigning good and bad. We're really just trying to bring those queries more to the forefront and more into immediate consideration. The other thing I would point out is that if the writes are bad, you're going to kind of know that the writes are bad along this process as you go through, because you're going to see the bad performance. That tends to get people's attention, right? So if you take care of the reads, my experience is the writes kind of take care of themselves. So again, why focus on read workloads? So if we think about this just from a philosophical perspective, for most systems, reads tend to be the locus of value. That tends to be the thing that really is the intrinsic value of the system. I want to be able to put money into my bank account, but if I can't read my bank account balance, all the writing into that bank account is meaningless. It's only the reads, right? So think about that. See how that idea fits with you. Now, you may be working on a system where there is an intrinsic value to a write that can't be read. And if you have one of those systems, good for you. Like that's very creative. And I'd personally, like, I'd love to hear on Twitter what you're doing, or what more of what the context is, just out of my own sheer curiosity. But 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 if you think about this in most systems, if you think about this from like the Toyota way, or from a manufacturing perspective, kind of cost benefit analysis kind of perspective, the rights do not matter. It's the reads that matter, that the reads are proper, that the reads are what you expected, that you're getting out of the system what you hoped to get out of the system. So from that Toyota way kind of classification, rights are just a cost. They're not an end to themselves. They are a cost of supporting those read workloads. If I haven't won you over completely on just the philosophical merits of that argument, let me also remind you that different databases for a long time have played all kinds of different tricks to accelerate read performance specifically. There's only so much that you can do to accelerate writes. But when it comes to reads, man, there's all kinds of amazing things that you can do. And we're used to seeing that in database land. So we're even used to the database vendors putting a premium on accelerating reads, making those reads more meaningful. Again, reinforcing this notion that reads really are the locus of value for most database management systems. Indexes, classic example. We're going to do a bunch of extra writes, not even knowing if we need that, because if we need them at query time, we're going to have those indexes to accelerate the reads. Replication, we're going to copy this data around, because if there's a failure or to increase performance, we want to ensure reads, either as an insurance policy or to boost performance in a linear and scalable way. So these are all all around this idea that rights are the cost. Rights should not be the goal. So don't fetishize them. Don't focus on your right performance to the detriment of everything else. It's really, if you can only focus on one thing, focus on read performance first, and that's an opportunity to get in better water. And we'll show you some really good examples of how. All right, so let's try to sum that up. So on one slide, I can give you what we're calling a QueryFirst method for database selection. And so this is not a recipe where step one is somehow magically pick a database out of a hat from that giant, because we haven't shipped the magic 8-ball yet. We're going to have to do the magic 8-ball, because I just had way too much fun coming up with entries and designs for the magic 8-ball. All right, but barring having that, here on one slide is a way that you can identify what's the database that's going to work best for you, or databases, plural, that will work the best for you. And it's pretty simple, fits on one slide. So the first thing you just start with is the data. So remember, this is like test-driven development. We want to start with the tests. We want to start with, well, what's the data in the tests? What's the inputs and outputs of the tests? So in this case, we want to have some seed data that approximates a working system. The accuracy here of the approximation is important. This cannot just be fake data, or you get fake insights, right? So it's really in your best interest to spend time trying to get your seed data to be the most accurate, most relevant that it could be. And that's not necessarily an easy problem, right? That is something that takes definite work and attention and energy. But like a lot of things in engineering, garbage in is garbage out. So what you need is just a really specific target. So we're not thinking best case data. We're not thinking worst case data. We're not thinking about data from a QA point of view, like what breaks the system or what are the edge cases that we need to, like all that comes later, right? What we're thinking about at this point is, how do I most accurately, what I think would be a complete working system, and let me have the actual data set to go with that, so that I can take an experimental approach and an empirical approach. The second thing I'm going to do, now that I have that data set, is now I can say, well, based on my data, I can imagine, well, here's like what it would look like on Cassandra, and here's what it would look like on Redis, and here's what it would look like on SQL Server or Postgres. You can now think about the structure of that data, how that's going to map, the indexes that are going to be available to you, and how those choices between platforms now, you're more than likely going to find there's more than one database that will work for that seed data, and that's okay. You're on the right track. You've already been able to eliminate a lot of the things that wouldn't have worked, obviously, because you're working backwards from what your seed data actually looks like. So now you can take that experimental approach. Let's just take a couple of databases, gen up some SQL real quick. We're not going to try to like build a working system on this. We're just trying to fake it. We're just trying to get enough experimental data about our seed data set that we can start to understand how these different databases might perform to us, just at like an order of magnitude kind of level. As we go more down with that, we're going to select the best database. I just keep using that pun. I actually wasn't thinking about it when I was writing the slides. But you're going to select the database that has the best workload fit, because once you get to this step 3, you're going to be able to say, well, for all the read queries that I want to run, well, here's how many of those operations per second I'd like to do, or here's how many seconds it takes to run that particular query. But and you'll know like which of those need to be super fast and which are super slow. You're already kind of fitting the order of magnitude thinking to this. And then you can immediately say, well, based on the experimental results that we have, like which of those feels like it's the right order of magnitude? Because I might be able to shift that I might be able to use a trick or two and shift it by 1 order of magnitude. But if I'm really looking to shift it by like 2 or 3 or 4 orders of magnitude, like I'm going to have to be a progressively better engineer to actually be able to pull that off, right? So again, this is a more empirical approach. We just want to work backwards from the operations per second numbers that we're getting out of the different databases that we're trying. Once you're happy with all of that, then you can start to optimize for loading and maintaining data on the platforms that seem to be working the best. So again, this is a query first way of looking at this, because normally with a capture first approach, you'd be starting on step 4. Even if you didn't mean to be optimizing, you probably are. Like you just can't help it. You're thinking about doing the inserts, and then you're thinking about optimizing the updates, and then you're thinking about optimizing the deletes, and then you're thinking about the transactions, and then you're thinking about the relations. And what did we forget? We never ran a query. It is so easy to fall into that gravity well. And I'm going to give you my own example of how I even fell into that myself with Resurface, even knowing all of this, and spent my entire career trying to apply these same kinds of techniques. It is still so easy to fall into thinking about optimizing the loading and the maintaining of the data before you've really truly solved the problem of read workload to database fit, and really making sure that is solid. Now, it may turn out as you go through this that there's no single database platform that is a perfect match for your different read workloads. That's a very real thing, right? That everybody has to, almost everyone has to contend with at some point or another, and that's okay. So, but this is a jumping off point that comes at the end. It's not, again, this is not something that you put at the beginning. You don't just grab Kafka at the beginning and say that's what we need. You need to be thinking about your read workloads first. You need to be starting at step 1, coming down to this. So if you do hit the step 5 and you say, well, part of my workload just really fits better on Postgres, and part of my workload really fits better on Iceberg, and I can't really jam all that together. So I'm just going to have one foot in two canoes. How am I going to do that? If I know I'm going to be in a situation where no single database platform is a perfect match, then that's okay. You're either going to use a distributed query engine, something like a Trino or a Presto, to bring that data together, or you can replicate that data through queues using something like Kafka or Pulsar or RabbitMQ, get that data replicated through to the systems where it's needed. Or you can consider using some other tricks, which I'm actually going to show you a few examples of some of those other tricks that you could think about. And that's it. There's no step 6, there's no step 12, there's no other slide that goes with it. That's the whole QueryFirst method for DB selection in one slide. And again, the big takeaways here is it's like test-driven development. You're starting with the data. That's why you want to start with accurate data. You want to work backwards from that, work backwards from what you know about your data in your domain, and then fit the databases and data stores to what you think you know, and not the opposite way around. And if you can, defer that complexity around doing a distributed system or using a queue-based system until you're really sure that you need it. And that'll keep you on the better path, especially when confronted with the huge number of database choices that are out there. So again, this is all about a process for picking a database as much as picking the right ones and making sure that you have the right outcome in the end. So here's an example kind of that kind of thinking and that kind of foibles in action. And this one, you know, it's easy to share because it hits super close to home. So this is from Resurface Labs. That's us. And in our use cases, we're building a database that is specifically designed to handle API traffic. There are databases for time series and for graphs and for columnars, and there's all kinds of different databases that are out there. There isn't really a database yet that's really designed specifically around this kind of data, and that's what we were out to do. We're out to do something that really hasn't been done before, and we're trying to do something really, really clever. And as far as our V1 product went, all that cleverness that we had, and even knowing everything that I took you through in all the slides up until this point, like, did not keep us from tipping our whole boat over and everyone ending up in the ocean. So we started off with our V1 product. We're a startup. We're a relatively young company. We built our whole product around Presto and Pulsar. We really obsessed around the right performance. You know, we couldn't help it. By the time we get as far as we're actually loading real customer data into it, right? Not our test data, not our synthetic benchmark data, but like real actual customer data and the shape of it and what that actually looks like. And then the actual queries that they want to do against it. We realize, oh my God, this is terrible. This is never going to work. Our read performance was just horrible. And whenever the subject of our horrible read performance came up, we would revisit the fact that we had to choose Pulsar, we had to choose Presto. That was the choice that we had made, and we just had to stick with it. We just couldn't afford to start over or whatever. It was really hard, right? And I'm sure other folks on this call, I hope, have had similar experiences, and it really sucks. Like, especially being a QA person or on the business side, and you're just sitting back and you're going, wow, for all this energy that we put into this thing, we can't get the data out that we'd hoped. Like, that's a bitter pill to swallow. But what we really didn't have was we didn't have the data. That was our single biggest problem in this whole thing. When we finished that first that V1 product and we got to this place, well, then when we went to start our V2 product, we stepped back from that whole thing. We said, all right, well, we know the implementation that we had was not the one that we want, but we actually know what the data looks like. And in fact, we have a year's worth of data. We have this really good codex. Now we can work backwards from that. So we threw our whole existing implementation out, and we took that year's worth of data, that codex, and we said, let's look at this. Let's define those queries that identified the failures and the slowdowns and the threats and the actual cases that we wanted to solve for. At this point, we had shifted from Presto to Trino because Trino has really taken over as the new Presto and gotten more of the momentum. And so we'd shifted over to Trino, and we were trying the memory connector in Trino because we just thought, like, well, let's start with an in-memory database, because whatever we're doing in memory, like, what can't get faster than that? If we can make that work, then we'll work backwards from that. We'll figure out, we'll see what that teaches us. And what we realized about the in-memory, the potentials for in-memory was awesome. Like, this is that we wish we had those queries. Like, we finally had a clear line that we could say, yes, if the system worked like that, we would really have something that was shippable. But the implementation around the Trino memory connector itself, that wasn't shippable. So for the first time, we knew, like, well, that's the performance characteristics that we want for the exact kind of data that we want to process. That's what we want to deliver. For the first time, we could really see it. And we knew what those benchmarks looked like from a very specific operation per second benchmark that we could compare against the Trino memory connector anytime we wanted to. Then we tried to replicate that performance with Redis using Trino. We got way too much network time because even though Redis is in memory, you're spending too much time going back and forth across the network. We then moved that to local CSV files, better, but still not very efficient. We ultimately ended up, in order to satisfy our read characteristics, we ultimately decided that building a custom adapter or a custom connector for Trino was the best way to solve the problem. If you had asked me, even at the start of the V2 project, is the solution in terms of storing the data and doing the data architecture going to be binary files read with a custom connector for Trino, I would have given that a very low probability because it's so weird and ornate and specific. But in our case, it was exactly what we needed to do. And the only thing that was going to lead us there, despite all of our cleverness and really immense amount of time and energy that went into this, the only thing that ultimately gave us the right result that we could really be proud of was working backwards from the read characteristics from this query first approach. So it's not just about being a great database architect or not so great or whatever. It's really about putting the time in, putting the energy in, being able to frame this in terms of a very empirical problem to solve, and having benchmarks to lead you, and then following where the data takes you. It's not easy, but it's easy to get your head around how to sequence those kinds of activities. So what does this mean now? So hopefully I've convinced you that focusing on reads and taking that query first approach is an interesting way to crack some of these problems, especially the problem around database selection, if not other kinds of database optimization problems. So we can now go back to that list of 370 databases that we started off with, and at least now we can simplify the problem down a little bit, because we can say, well, so really, like, we're looking at this giant diagram, like that part hasn't changed. But what we really need to do now is we can just focus on the read performance and the read characteristics initially to know where to start. Right. So part of the story I just told was we went to Trino and then we went to Redis and then we did this. And but how did you do that? How do you like pick at that level? So I want to make sure I'm answering that question. And that's what we're getting down to ultimately with this one slide that I'm going to show you about how to navigate this whole picture here. So we're simplifying this. We're just going to focus on the read characteristics of all these systems. How are these systems grouped in this topology that we're seeing here? They're being grouped algorithmically. And so apologies for this, but at some point we're gonna have to talk big O and data structures, right? But this is the only slide where I'm gonna do this, and it's just for a minute or two. I know this stuff gives me a crazy headache. So however you're feeling about big O notation right now, it's totally fine. We're gonna get through it. This is not the focus of this talk. This is not the one slide that you need to know, by the way, that's coming up next. But just to say that there is a quantitative basis for grouping these things together. This is not just a way of storytelling, right? There really is solid math behind these kinds of groupings. And this is what you'll see in some of the classic literature around this. We're going to be looking at caches. Those have big O of 1. We're going to be looking at B trees. We're going to be looking at columnar stores. We're going to be looking at LSMs. We're going to be looking at map reduce, right? And I don't even want to go through this like any more than to say, yeah, that's out there. And if that helps you, that's great. But we're moving on because what this doesn't tell me is, well, how does this map to a workload that I would imagine myself doing against one of those databases, right? What I really need to know instead is I don't need a big O for the algorithm. Like I need a big O for the types of read IOs that I'm doing. So what I'm showing here is we can start with key value kinds of workloads, and that's like 1 IO. Then you're going up to 10 IOs, and then 100 IOs. It's log scale, right? By the time you get down to a DSS query, you're talking about millions of IOs that you'd be processing to do one of these queries, right? And I could spend more time going more into detail about, well, what does each of these workloads represent? I'm giving some kind of short descriptions here, which I'm not going to go into all the details. The most important thing, though, is that these are log scale, and that these are things that you're going to commonly find in your application. I need to do a lookup on something. I need to do a join on something. I need to do a transaction. I'm trying to do some reporting. These are more application-oriented patterns, but we can still be empirical and we can still attach an order of magnitude kind of weight to these. So this is the one slide that then allows us, if you take everything I've said so far, you smash all this together, plus like another 10 years of knowledge about and research about what all these different databases do. When you sit down with your favorite database architect and they are walking you through this process of mapping workloads to databases, this is the picture that they're carrying around in the back of their head. And they're kind of doing this on the fly. And so what we can do here is for each order of magnitude, each kind of different read workload that we might think about, we can see that of all the different data stores that are out there, there's one of them that really knows how to party when it comes to that particular kind of thing. And what I've tried to do here is just assign one in each category that really is a clear winner. And you know, obviously there's a little bit of hand waving here to get something that fits nicely onto one slide without being overwhelming and still trying to give you a decent cheat sheet. But these are the same kind of patterns that you're already going to recognize if you've read about them, but you just may not have thought about it being laid out on a log scale like this before. You know that caches are tremendously good about just grabbing one thing, grabbing one thing, grabbing one thing, grabbing one thing. You know, the B tree databases, they're the kings of indexes. They're the kings of joins. We know that columnars, where you're pulling back just a few columns at a time, that those can be really amazing. Then there's stuff like MapReduce, you can do almost anything. But the number of IOs that you're talking about doing with MapReduce is enormous. And actually, it's at the bottom end of the scale that gets triggering for me because these are exactly these super columnar queries are exactly the kinds of queries that we're trying to run in our database. And I think there's other systems like that that are really trying to push the boundaries of using all the data all at the same time, which looks something like this. I've got all this crazy amount of data out there, and I'm trying to find these intersections, these very narrow intersections, where I've got API failures and API customers, and that's where revenue is being lost. The subsetting, being able to use all the data at once. There's some amazing opportunities that are out there, but you really have to know where your workload falls into that order of magnitude perspective. Something that's, millions of IOs, that's the only solution for one kind of case, is not going to be the right solution for other kinds of cases. And then there's some that you just flat out want to stay away from. If you're using a B-tree database, for example, or even a columnar database, and you're really trying to use all the columns that you have available to you in a query, all rows, all columns, something like this, forget it. All your indexes go out the window. You're going to have a really bad time. The way that you figure out, but again, the way that you figure this out is not so much like picking a database at the top. This is query first. So it's really about thinking about your workloads, thinking about your distributions of reads. How do those cluster together? How many of this do you do versus that many? And just really getting a sense of what those workloads look like. And then work backwards from there to the data sources where you know are really going to be able to do that well. It's as simple as that. Work backwards from the workloads. Now, of course, there's more complicated tricks that we get into this, and some of these things I'm going to just hint at because there really isn't enough time to get too far into too much of the details about any one thing here. But I wanted to give you a little bit of extra color because it's not always just this simple, right? Sometimes you can look at this and you can say, yep, Postgres is fine. It's going to do everything we need it to do for the scale that we're going to have for the next year, and that's great. Let's just do that. And then you throw some Parquet on top later on, or whatever the next phase is. That's totally fine. If you're looking at a picture like this though, and you're already saying like, well, I know there's no one database that can do it all. How do I work backwards to that choice? That's okay, because that's still part of what we're giving you here. So your main choice there is either going to be you're going to want to do some queues, you're going to want to fix it with queries, or you're going to want to use some other trick to try to get all those reads in one place if you can, or try to manage that fan out. The queues one is the one that has really become a lot more popular in the last few years. Kafka is a great thing. By all means, if that's the right thing to use, then great. I would caution anyone, though, against thinking about Kafka as a database. It's not a database. It doesn't do read workloads very well. It does a read from the top of the queue very well, but it does not do a read of the queue very well. Kafka and queues are about copying data between machines. They are not query engines themselves. But if you know that part of your data fits really well into Postgres, and then a bunch of your data is just going to fit better in Iceberg, you can put a queue in the middle. You can now do some of your reads off of Postgres, some of your reads off of Iceberg, and you'll be a happy clam. The other way to solve that, and these are actually equivalent implementations to a largely arguable degree, would be to use something like Trino. So instead of kind of statically declaring how that data flows through a queue or through a set of ETL pipelines or data ingestion pipelines, we're going to do this dynamically. We're going to run our queries against Trino. Sometimes that data may come from Postgres. Sometimes that data may come from Iceberg. Sometimes that data may be joined from both Postgres and Iceberg at the same time in return. Trino can also do the mapping. Sometimes I'm doing an insert into Iceberg where I'm selecting from Postgres, and there actually isn't like a queue in the middle. It's that you're running queries. that move the data around. So this is just classic push versus pull in database architectures, right? Queues can be great, but they're not the solution to everything. You can get to very complex systems very quickly through introduction of queues. You can get out of order things, you can get race conditions, there's all kinds of other things that could happen. So I'm actually increasingly more of a fan of the Trino approach, where Trino is not a database, it's a query engine, and it allows you to push the queries out where they're needed and bring that data back in. All right, and then if the queues and the query stuff, if you still can't get to the finish line with that, and you still have an order of magnitude shift that you have to make in your IOs, then that's cool. Track me down on Twitter. Let's talk about what the next post is going to be. But here's just a couple ideas to get you started. Maybe just some things to get you thinking about. One of the classic ways to get an order of magnitude shift in your read IOs, in your read workloads, move that data in memory, eliminate the device IO, or move to a local embedded store, get that data off the network. So a lot of these databases, they either have in-memory modes or they have local embedded modes. So explore those. Explore kind of the federation, load balancing being done at a different layer, putting more of the data and more of the compute at the same place. Again, Trino is a really great way of doing that if you're looking for a toolkit around that. Those are kind of some classic ways. Some other ways that are a little bit hotter are use computed or virtual columns. A lot of times we're waiting on IOs, right? So if there's actually things that you can compute at query time while the system is waiting for those IOs to come back and doing less IOs, again, that query first approach will tend to lead you in that direction faster. You'll tend to see those opportunities quicker. And in our case, with our V2, we actually write a lot less data than we ever wrote with V1, which is crazy because everything we did with V1, we were trying to optimize the writes, but we just really hadn't understood the possibilities of optimizing the reads yet. We moved a lot of our stuff from capture time processing to query time processing into virtual columns, into virtual views. Now we just don't need to wait on that data, and we never needed to store it to begin with. It's just eliminated writes that went away. It was waste that we didn't need, but this is how we found it. So that idea of optimizing the storage, optimizing, how much of that is actually persisted versus virtual, or whatever the combination of that is, that's a whole nother thread of things to follow. Then there's just some other just like pure badass techniques. These are things that you'll see other folks talking about, but using immutable writes to safe transactions, for example. This is how you take something like Cassandra, but you use it as a transactional store, because you just read all transactions within a window, and you compute a final result against everything that you have. You can create some transaction boundaries there and get transaction characteristics out of a database like Cassandra that doesn't natively support those concepts. Another popular construct is use the page cache as a form of in-memory storage. Kafka does this really well. When you're reading from the top of the queue, you're reading the data that was just written. So it's always in memory. Kafka operates as an in-memory database a lot of the times, even though it isn't strictly an in-memory database. We do the same thing. With Resurface, we also do in-memory storage the exact same kind of way, and we use Trino to push those queries close to that in-memory database and get really, really lightning read performance out of our system, because that was our whole goal working from this query first point of view. So that was a lot. Wow, there's a lot to unpack there. Thank you for going with me on this journey. I think what you're going to find as you start to apply more of these query first methods, the possibilities here really are endless. you'll go back to DB engines, you'll go back to Martin's book, you'll see those topologies about all these choices that are available to you. And hopefully you come back to that with a little bit more enthusiasm than dread next time. And you'll have those cheat sheets and you'll have those single page methods that we showed here to help you guide on that. And I'd just like to say thank you to everyone at Percona for giving me the opportunity to share these experiences and share a couple laughs with you. And would love to hear your questions. I'm easy to find at Rob from Boulder on Twitter or Rob at Resurface.io on the interwebs. Thanks so much.